This conference will now be recorded. This conference will now be recorded.
Hello everyone. So today the topic that we are going to discuss, solubility equilibrium of sparingly soluble salts, then solubility product. There will be related problems, and if time permits, then common ion effect in solubility product, that also we can discuss. So different types of equilibrium we have seen. Today we will see that for sparingly soluble salts. But before going to sparingly soluble salts, first we have to know, that is how we will be able to understand whether a particular salt it will be soluble or not. Then the question of sparingly solubility exists. Okay, so first we will see how to know whether it will be soluble or not, or it will be highly soluble, or it will be having low solubility. So there are some ionic solids that are highly soluble in water, but not all of them. And even there are some salts, they are not at all soluble. So you can say that they are actually insoluble in water. Now, it depends on some factors. And what are those factors? It depends on lattice enthalpy of the salt and hydration enthalpy of the ions in the solution. So here we are seeing two terms, though these terms we have already discussed in other unit, but here we will see it again, that lattice enthalpy of the salt and hydration enthalpy of the ions in solution. Now this hydration enthalpy, it can also be called solvation enthalpy, depending on what type of solvent you have taken. So we can call it hydration if the solvent is water, and mostly we take water as solvent. So that is why the term we can use hydration enthalpy of the ions in solution, that is solution of water obviously. So lattice enthalpy of a salt, that is defined as the energy required to overcome the attractive forces between the ions in the gaseous state. So suppose you have taken some salt and there is some ion. I am simply taking the salt Kb. So if there is an ion present A plus and B minus, and they are in gaseous state, so in bracket I am writing the physical state G, which means the cation and anion, it is in gaseous state. So from the lattice, when you are breaking these cations and anions and you are bringing them, that is, they are now isolated gaseous ions. So for this process, the energy that is required, that is actually lattice enthalpy. Fine. And what about hydration enthalpy? Hydration enthalpy, we can use this term only when solvent is water. Or otherwise, if you want to use the general expression, then you have to use the term solvation enthalpy. Okay. So this hydration enthalpy or solvation enthalpy, that is the energy released during the interaction between the ion and solvent molecules. Now, to understand that, you have to consider the ion as if they are already present in solution. Now, when they are present in solution, several water molecules, I am taking water because that is the most common solvent, several water molecules, now it will interact with these cations and anions. So this cation and anion, now they will be surrounded by water molecules and it will result some stability. So that is why in this case, when the cation and anion, they are surrounded by water molecule, there will be some energy released because now they are in solvated condition, and solvated condition means now they are in stable state. So that is why some energy will be released. This is exothermic process. Now the amount of energy released for this process, that is actually defined as hydration enthalpy. If you look at this pictorial diagram, here we have taken the very common salt, which is sodium chloride. In bracket, its physical state is mentioned S. Now, come to this side. Delage lattice standard state. Okay, so this is the lattice enthalpy. So see, from NaCl lattice in solid state, when you are making these individual cations and anions, now you are breaking the lattice, and obviously for that process you have to provide some energy. And now the physical state is G. So Na plus in bracket G, Cl minus in bracket G. Now from these gaseous cations and anions, you are adding some water, and now the physical state G is changed to Aq. Aq means they are now solvated. So from gaseous isolated cation anion, now they are in which state? Now they are in solvated state. They are surrounded by water molecules. If I am writing Na plus, they will be surrounded by several water molecules. So this oxygen site, that will be towards sodium because it can donate lone pair towards sodium. Similarly, if you take Cl minus, now hydrogen atoms should be facing towards chlorine because chlorine is carrying some negative charge, and in water the positive part is basically hydrogen. So in this way they are surrounded by water molecules, and for this process the amount of energy released, that is actually del H. HYD means hydration enthalpy standard state. Okay, now you are moving from state 1 to state 2, then state 3, but you can also move from 1 to 3 directly, and in that case the enthalpy change that is involved, that is known as del H SOL. That means it is enthalpy of solution. So directly if you are, that is rather than first making Na plus G, Cl minus G, and then going to aqueous, if you are directly doing the process, then NaCl solid directly to aqueous. So in this case the enthalpy change, that is known as del H solution, that is solution enthalpy. So as we know all the enthalpy, it is a state function. So that is why from 1 to 2, 2 to 3, for these two processes, if you add the corresponding enthalpy, then you will get the total enthalpy change. So that is why the relationship between these three terms, del H sol equal to del H lattice plus del H hydration. Okay. Now del H lattice is always positive because you are breaking some lattice, so you have to provide energy. Then a del H hydration, it is making the system more stable, so that is why it is negative, that is energy is released. Now the overall process, that is del H sol, as it is summation of these two quantities, obviously if the numerical value of del H lattice is lesser than del H hydration, then only this overall quantity, it will be also negative. That means del H solution, in that case it will be negative. Okay. Now when this del H solution is negative, then only solubility of the salt is possible, otherwise it will not. So more it will be towards positive value, then gradually the solubility will be decreased. So if the salt is to be dissolved in the solvent, that is water or any other solvent, mostly water, then its solvation enthalpy or hydration enthalpy, that should be greater than lattice enthalpy. That means here we are focusing on the numerical value. The numerical value, that should be, that is the numerical value for hydration enthalpy, that should be greater than the numerical value of lattice enthalpy, because this is negative. So if its numerical value is high, obviously then overall change in the enthalpy, that will be negative, and in that case the salt will be soluble, otherwise it will not be soluble. Okay. Next we will see that depending on this type of solubility, that is different types of solubility may be there. Suppose some salt is very soluble, some salts are not soluble at all, and there may be some intermediate cases. Now when you have any salt which is not very soluble, that is not like NaCl or KCl, then there will be, that is easily you can make saturated solution, because if you want to make saturated solution with sodium chloride, that is simple table salt, day-to-day life we use. If you use that salt to make saturate, it will take a huge quantity because its solubility is very high. But if you take any salt whose solubility is not very good, then easily you can make the saturated solution. So how you will understand that it is saturated? So once it will reach the saturation state, then further addition of salt, it will be precipitated. So maximum limit is reached. Now when you already reach the saturation state, that is the solution is already in saturated condition, under that condition the concentration of the substance, that is the salt that we are dissolving, that concentration, that is already when saturation state is reached, under that condition the concentration of the substance, that is called solubility, and it is denoted by capital S. And remember, it is obviously at a fixed temperature because it is temperature dependent. So you cannot compare the solubility of two salt at different temperature, because then the comparison will not be correct. So only when the temperature is fixed you can compare solubility of different salts. So it is the concentration when saturation state is reached. So just like concentration, you can also express it as moles per liter, or you can express it as grams per liter. Mostly we express it in moles per liter, and obviously at a given temperature. Don't forget that. Sometimes if temperature is not mentioned, by default you can consider as if it is at room temperature. Each salt has its characteristic solubility and it depends on temperature. Okay. So suppose you have taken 4 to 5 salts, temperature is fixed. Each one of these salt will have different value of solubility, and that depends on how soluble, that is whether their very solubility is high, low or intermediate. Depending on that solubility value, that will also change. Now how to know, that is what is the measuring scale based on which we can decide that yes, this salt is soluble, this salt is not so soluble. How to decide that? So for that there is a specific values. If the solubility falls in that particular range, you can call them, yes, it is soluble. So see, in this table we have these ranges. There are total 3 types: type 1, type 2, type 3. So type 1 are those that are very soluble. So solubility is greater than 0.1 molarity. An example is sodium chloride, or you can take any other salt like potassium chloride, and that is mostly alkali or metal or alkaline earth metal salts. Now what about the type 2? If the solubility is obviously lesser than 0.1 but greater than 0.01, if it is in this range, then we will call them slightly soluble. And if it is even lesser than this, and there is no limit, that is towards the low side, there is no limit. So now we can call them sparingly soluble, that is very low solubility. So we have 3 different examples under these 3 types. Calcium phosphate, that is the example for the type 2, and AgCl, that is the example for type 3. So AgCl, probably we you know that chloride minus ion, when you have any solution which is containing chloride minus, and in that solution if you are adding some Ag plus salt solution, for example you are adding silver nitrate, then AgCl is precipitated. You can see the precipitate in the test tube. Now why it is possible? It is possible because AgCl, its solubility in water is very low. So as solubility is low, as soon as in presence of Ag plus Cl minus the salt is formed, it will be easily precipitated, because its capacity to remain as Ag plus cation, Cl minus anion in water, that is surrounded by water molecules, that capacity is very low. So that is why this salt is example of sparingly soluble salt. Its solubility value, that is this capital S value, it is lesser than 0.01. Okay. So based on this scale, we can define sparingly soluble salts, and our focus will be on this salt only, not type 1 or type 2. We are talking about type 3 only. So here we will see what type of equilibrium exists in the solution of sparingly soluble salt. That is the topic, solubility equilibria of sparingly soluble salts. So there will be some equilibrium between the undissociated salt, suppose undissociated AgCl in the left hand side, and in the right hand side the very low fraction of HeCl, that is in Ag plus form, Cl minus form, that is in the right hand side. And so between these two there is some equilibria, and that equilibria is solubility equilibria of sparingly soluble salts. So sparingly soluble salts, here you can see some more examples: PbSO4, lead sulfate, barium sulfate, etc. They have negligible solubility, or you can say practically insoluble. The value is so low in water at ordinary temperature. Now the amount of such salts getting dissolved, it is so small that their saturated solution you can consider as if it is extremely dilute. That is, the once it is precipitated, when you are making the saturated solution, the upper transparent filtrate part, that is actually the saturated solution, and that is extremely dilute because the amount of cation and anion generated from these salts, that value is very low. Now here we have these three examples, but in general if we want to express how they are dissociating and what will be their solubility equilibrium, then we will consider this general salt AX BY, in brackets it is written physical state A. So AX BY means what? X number of cation A and Y number of anion B. X and Y may be any integer. Okay. Now once it is in equilibrium, from this AX and BY, now X number of AM plus, what is small m? Small m is basically the charge of the cation. Now you can compare it with BaSO4. Suppose I am writing here BaSO4. So in this case, BaSO4, this part is A, this part is B. Now here, in case of BaSO4, X is 1, Y is also 1, because both cation and anion, they are present just 1, right? Now once it is dissociated, barium, it will have charge 2 plus. Just compare here, X value is 1 and M value is 2. So it is in aqueous state. Then sulfate, its ion charge is also 2 negative. So in this case, the small n, that is actually the charge of the anion. So here you can understand n value is 2, m value is also, but this is negative charge, this is positive charge. And one thing that has to be, that is this relationship, it will be true always, because otherwise the total charge, overall charge of the salt is obviously, it has to be neutral. Now for the salt to be neutral overall, obviously this X into M plus, that is the total amount of positive charge, that must be equal to total amount of negative charge. In this case, M plus value is 2 and it is 1 into 2. Here also it is 1 into 2, because in our case X, Y both are 1, 1 and N is 2, N is also 2. Okay. So in this way, in general, we can express the equation for sparingly soluble salts. X number of cation A will be produced carrying charge M plus. Y number of B anion will be produced carrying the charge N minus. Now we will see the equilibrium. That is the K equilibrium we will derive. So the equilibrium between the sparingly soluble ionic salt, that is this one, and the saturated aqueous solution. So in saturated aqueous solution, these cation and anions, they will be present. Now the K value for this equation, the same way as we represent, that is the concentration of Am plus to the power x, because that is coefficient, so it will be now present in power. Y is the coefficient because Y number of Bn minus anion present, so that is why here it is present, divided by Ax By. Now this value, as very few fraction of Ax By, it is in dissociated state. So obviously, as if this concentration of Ax By is almost constant. So this approximation we can apply. So that is why now this denominator, if you bring it to the left hand side, that is K into some constant, you will get a new value which is called KSP. SP means solubility product. Now see what we have written in place of this, that is Am plus, concentration of Am plus, we have written X into capital S because of this relationship. So this capital S, we have already seen the definition. It is basically the solubility. So this capital S, it is present in the expression of Am plus as well as in the expression of Bm plus, provided the coefficient is present. Okay. So this is the expression for KSP. Now how we can define it? In a saturated solution of sparingly soluble salt, the product of molar concentration of ions, that means these two, raised to the power of its stoichiometric coefficient. So this is the stoichiometric coefficient raised to the power, right? In a balanced equilibrium equation. So this equation that we have taken here, based on which we have the expression of KSP, that must be balanced, because if it is not balanced, this relationship will not be applicable. So first of all, it has to be balanced. You have to write it properly. Then only this definition we can apply. So this is this product is constant, and this product we express by KSP, and the product is called solubility product. Okay, so this is the expression of solubility product. Now one more expression we will see. Remember when we have discussed, that is when we have started this unit, in that case K equilibrium, how we express like this, that is KEQ. Then also we have seen one more expression which is known as Q. So Q expression also we have used during normal equilibrium. Right now we are talking about ionic equilibrium, but when we have discussed, that is all the classes we have taken on normal equilibrium, then we have seen this Q term. So this Q, it has same meaning just like K equilibrium, but we use it only when the equilibrium condition is not reached. Otherwise K equilibrium, how we express it? Concentration of product divided by concentration of reactant. So Q also having same expression, but what is the difference between these two? Q you can use only when the system is not under equilibrium, then only you can use Q. So similarly here also, when we are talking about solubility equilibria, KSP you can replace with QSP. Now it is called ionic product, not solubility product. But when you can use it? Only when the concentration of one or more species is not the concentration under equilibrium. So if the system is not that is not yet reached equilibrium, under that condition you can use QSP, not KSP. Okay. So only under equilibrium condition these two values will be equal, but otherwise it will give you the direction of the processes of precipitation or dissolution. So what it means? It means under equilibrium these two are okay, these two are equal, but if equilibrium is not reached, then the significance of QSP is that from this QSP, that is ionic product, you will be able to predict the direction of the process, whether the system, that is from the ionic product value, you will be able to understand whether the equilibrium will be shifted towards left hand side or it will be shifted towards right hand side. So when it is moving towards left hand side, there will be some precipitation because it is now going towards undissociated salt. But if it is going towards right hand side, that means it is going towards dissolution. Now how to know that? That depends on this summarization. If these two are equal, obviously equilibrium exists, solution is already saturated. But suppose this ionic product value is greater than KSP, because KSP there is a database for different salts. You can know, suppose you already know the KSP and you have taken some salt, you know the ionic product and the system is not yet reached equilibrium. Under that condition, QSP value, if it is greater than KSP, then precipitation will start. That means now the ionic product Remember the expression we have just seen in the previous slide. That product, if it is somehow KSP, to make the KSP value, that is as KSP value is fixed, so QSP cannot be greater than this. But if somehow it is high, that means now precipitation will start, and QSP value greater than KSP means it is now super saturated. But if it is lesser than KSP, that means now still some more salt molecules, they can be, that is dissolution is possible. So in that case, no precipitation will occur and the system is still, it is unsaturated state. So now you can say that it will move towards right hand side. That means some dissolution is possible. So in the second case, some more dissolution is possible. But in the first case, if QSP is greater than KSP, now precipitation will start. That means now this equilibrium will shift towards left hand side. Now this is also kind of Le-Chatelier principle, because to keep the value of KSP fixed, if there is some excess of any of these concentration of cation and anion, then the system will manage it in such a way so that it can reach KSP, and that is actually equilibrium. And once this condition is fulfilled, now there will be no further change and the system, it is already under equilibrium, solution is saturated. We can represent it with this pictorial diagram. So here we have ionic product in the y-axis, change in amount of dissolved solid over time, that is in the x-axis. So when Q is equal to KSP, this ionic product value, it is parallel to x, there is no change. But suppose if Q is lesser than KSP, that means change in amount of dissolved solid over time, this will increase so that it can reach KSP. So ionic, see here, if you choose any point, here the value is this cutting here. If you choose here any point, change in amount of dissolved solid over time, it is somewhere cutting here. That means ionic product is gradually increasing. So it is basically this case. And the first line, it is QSP greater than KSP. That means with time, change in amount of dissolved solid, it will decrease, right? Ionic product is already than KSP, so it will be changing itself in such a way so that ultimately it becomes equal to KSP. So this is the pictorial representation of ionic product. So based on this Q and KSP, we have a problem here. So it is saying that KSP for the following dissociation. What dissociation? We have this salt, lead chloride, PbCl2. In bracket, it is S. And after equilibrium, we have Pb2 plus cation aqueous, 2 chloride ion aqueous. Which of the following choices is correct for a mixture of 300 ml 0.134 lead nitrate? So this is a different salt of lead, and we have 100 ml 0.4 molar sodium chloride. So you have, suppose in one beaker you have this solution, another beaker you have this solution, and now you are adding these together. So when you are adding this together, in this, from this solution you will get Pb2 plus ion, and from the second solution, that is sodium chloride, you will get Cl minus ion, right? Now these two ions together, it will make a new salt, which is PbCl2. Now this new salt is basically sparingly soluble salt, and its KSP value, you can see the KSP value, it is so low, 1.6 10 to the power minus 5. So KSP value for sparingly soluble, sometimes the power even becomes so negative, 10 to the power minus 13, minus 19. That means it is very, very low. So more negative will be the power of 10. That means solubility is also very low. So here we are mixing these two solvent, different solution. We are getting a new salt because of the reaction between these two salt, Pb lead nitrate and sodium chloride. Now we have to calculate what is the concentration of the cation Pb2 plus and what is the concentration of ion Cl minus. Now this is the molarity. Now we know when we have volume in ml and concentration in molarity, if you directly multiply it, you get the number of millimoles. So if we do so, what we will get? This is the volume for lead nitrate, this is the volume for NaCl. So total volume final, it is 400. So we can write that 400 ml solution, it contains 300 multiplied by 0.134 number of millimoles of Pb2 plus cation. Okay, this is the number of millimoles. When we directly multiply volume in ml and concentration in molarity, we get always number of millimoles. So 400 ml contain this number of millimoles. Then 10 to the power 3, that means 1000 ml, it should contain 400 multiplied by 10 to the power 3 millimoles of Pb. But in terms of moles, if you want to change millimole to mole, you will multiply with it 10 to the power minus 3. That means these two will be ultimately cancelled. And from this equation, the ultimate value you will get 0.1005. So it means that this number of moles present in 1 liter. So this is actually the molarity of Pb2 plus. Okay. Following the same method, we can also calculate the concentration of Cl minus ion. So in case of Cl minus, now that is same type of calculation we will do. 400 ml, it contains 100 into 0.134 millimoles Cl minus. Now if it is so, 10 to the power 3, that will contain divided by 400 multiplied by 10 to the power 3. But remember, if you convert it to mole, then it will be again multiplied by minus 3. So these two cancelled, and ultimately the value is 104. So it is 0.4. 0.4. So ultimately it will be 0.1. That is the molarity for Cl minus. Next step, if you follow this equation, then the value of, basically the value of Q, because it is asking which of the following choice is correct. It is not mentioned that it has already reached the equilibrium. So what we will do, we will basically calculate the value of Q, ionic product, which is Pb2 plus sorry, we will not write 2 here. This is the coefficient, we will write it here. Now Pb2 plus is concentration is 0.1005 multiplied by 0.1 to the power 2. So 0.1005 and 10 to the power 0.1 means 10 to the power minus 1, there is a power, so it will be ultimately 2. So if we want to compare it with this format, it will be you can change it to 1, that is if you shift this decimal 1.005 10 to the power minus 3. So now the power will change, and this value of Q, just compare with this one. This is basically greater than the Ksp value which is given in the question. So Q is greater than Ks. It is asking which of the following choice is correct. And here we have these three conditions, whether Q is greater than or less than, or whether it is equal. And the fourth option is not enough data, but we have enough data. And the second option, that should be the correct option, because whatever ionic product we are getting, that is actually greater than Ks. Fine. Next, here we have different examples of different types of salt. In the previous case, PbCl2, this is basically okay, so that type is not mentioned. The type is basically AB2. The recent problem that we have just solved, PbCl2, 1 cation, 2 anion. So this is matching with the formula general AB2. Similarly, we can have different types of other formulas. See, if it is AB type, it is AgCl. So in this case, AB, how we express KSP, that is if solubility value is given. In the previous case, we have directly calculated concentration. We have not used solubility, but now we will see how to use this capital S. So when you will write KSP in terms of capital S, that is solubility, not in the previous way. This is something new. When you will express it in terms of solubility capital S, then the term will be like this. So when you have any salt where 1 cation, 1 anion, that means the type is AB. If you have this type of salt, then it will be SS, because now in the medium, remember AXBY, that is the general expression we have seen, right? So X number of AM plus, remember this we have already done, Y number of BN minus. So here when X, Y both are 1, example is AgCl, then solubility will be simply SS. This is the simplest case possible. But suppose if it is A2B, now it will be 2A. Okay, I will write it in terms of Ag2SO4 directly. See if I am writing it in terms of Ag2SO4. That is silver sulfate. Now we have 2 cation, 1 anion. How you will write it? It will be Ag2 plus and 1 sulfate ion, 2 negative. So in this case, when you are expressing in terms of solubility, for both cation and anion, S we have to use. So here you will write 2S, here it is S. But when you will write the KSP, now it will be 2S power 2. Again you have to put it multiplied by simply S. Ultimately what you are getting? You are getting 4S cube. Similarly, when it is AlOH whole 3, now it is Al3 plus and 3HO minus. In this case, Al3 plus solubility capital S, but for each Al3 plus, if you compare with relationship with HO minus, for 1 mole of Al3 plus, there will be 3 moles of hydroxide. So that is why it will be 3S. Similarly, when it is, that is a Ag2SO4, for 1 mole of sulfate, you have double moles of Ag2 plus. So that is why S should be now 2S when you are considering it for Ag2 plus. Now, if you are thinking why we have not done it in this problem, but see, in this problem we have not used solubility. Directly we have calculated molarity. So this value of Cl minus that you have obtained, don't make it double, because with respect to Pb, if you are thinking that Cl minus is double, don't do this, because this concentration we have already obtained for Cl minus, it is already included, that is the information is already included that it is double. Don't do it separately. But when you are expressing in terms of solubility, that is this discussion, now you have to check that what is the ratio. So here cation and anion, it is basically 1:3. So that is why I have written S and 3S. Now when you will write KSP for aluminium hydroxide, it will be S multiplied by 3S. Now here we have coefficient, so that will be in the power. So 3 to the power 3 is 27 and S to the power 4. Similarly, when it is A3B4, there will be total, if you consider this salt, 3 Zr. Here the charge is 3 plus, and we will have 4 PO4 3 minus. Remember this charge, it is it is 4 plus. The charge when you multiply with coefficient, it should always be same. So 3 into 4, 12, 4 into 3, that is also 12. That means total positive charge is 12 plus, total negative charge is 12 minus. So in this Zr 4 plus. For 3 moles of Zr, we have 4 moles of PO4. That means if I am writing here 3s, it should be here 4s. Now 3s, it should be multiplied by 3. Then 4s, sorry, not multiplied, raised to the power 3, and this should be raised to the power 4. So ultimately 3 to the power 3 and 4 to the power 4, and total power of s is 7. So ultimately you will get this type of value. So these are the general formulas. The corresponding examples are also given. The first one simplest, then it will be A2B, or it may be AB2, it may be AB3, or it may be A3B. Different possibilities are there. Only 4 are shown here. So in this way we have to calculate solubility product. So here in this table you can see some examples, that is you can consider as if it's a database. Though there are so many salts, it is not possible to mention all of them. Only some common salts, their KSP value you can see. AgCl, look at the value, it is so low. Here lowest value you can see 10 to the power minus 36, it is very low. For calcium carbonate, it is very low. So among all these, mostly which one is having lowest? This one. So among all these, actually all of them are sparingly soluble, because they fulfill the condition but solubility value is lesser than 0.01. Remember the table, type 1, type 2, type 3. So when it is maintaining, that is following solubility 10 to the power lesser than 10 to the power minus 2, that is 0.01, then they will be under the category of sparingly soluble salts. So here we have some examples so that you can have some idea how the values are actually. So this problem here, the salt type is AB2. Solubility in water of a sparingly soluble salt AB2, capital S value given, which is 1 into 10 to the power minus 5 moles per liter. You have to calculate KSP. So AB2, how you will write it? It is basically 1A to B. Even if you do not write charge, it doesn't matter. So total negative positive will be equal. So solubility, it is S. So see, the relationship is 1:2. That means it will be 2S. So when you will write KSP, it will be S multiplied by 2S raised to the power 2. So it will be 4S cube. Basically, even if it is the other type, A2B, in that case it is 2 cation, 1 anion. In this case also it is same, 2SS, KSP is again 4S cube. So whether it is AB2 or A2B, it is always follow this 4S cube. So here S value is given, S value is this one. So 4 into 1 into 10 to the power minus 5 to the power 3. So it is 10 to the power minus 50. It is matching with the first option A. Okay. So it is very simple. Next we will solve, which is comparatively complex. You will not get so simple problem actually. Here we have 3 different types, AB, AB2, A3B. 3 different types of formulas. So this is for AB. The second one is for AB2, and the third one, it is for A3B respectively at same temperature, capital T. You have to find the solubility order of the salt in water at the same temperature in moles per liter. So KSP value, KSP1, KSP2, KSP3, 3 different KSP values are given. So for each KSP, you have to calculate the corresponding KSP value. So when it is type AB, then we have type AB2 and we have type A3B, right? So when it is AB, we know it is 4S cube. That means Ksp value 4s cube, that is equal to 4 into 10 to the power minus 8. 4 both sides cancelled, and s value will be root over 10 to the power minus 8, which is basically, sorry, it is 4 into, it is AB type. It is simple, it is simply a square. So it is simply root of 4 into 10 to the power minus 8. That means it is 2 into 10 to the power minus 4. So this is the value of S in the first salt. Now in the second case, AB2, now it will be 4S cube, 3.2, 10 to the power minus 4. So S, if you write it in this way, it will be easier. So what I am doing, 3.2 I am writing as 32 so that it becomes 50. Now S cube will be equal to 8 into 10 to the power minus 15. So S will be cube root. Now the calculation will be easier because when you have made it from 14, you have made it 15. Now it will be 3 times less. So it will be 2 into 10 to the power minus 5. And if you want to, okay, these two are same. 2 into 10 to the power minus 5. And what about the last one? The last one is A3B. And for A3B, if I write it like this, even if you don't have to remember the formulas that I have just shown in the previous slide, it is basically 3s and s. That means 3s to the power 3 and s. That means it is basically 27 s4. And that is equal to 2.7 10 to the power minus 15. So 27, I will write it 2.7, I'm writing it as 27 so that it becomes minus 60. So S4 is equal to 10 to the power minus 16. That means S is equal to 10 to the power minus 4. Okay. Now you compare these three values. Obviously, the maximum value, this is having lesser power, so it will be at the minimum end. So AB2 will be at the minimum, that is sure, and that you can find only in the last option, right? So this much information is enough to choose the correct option because in all other cases it is not at last. Now among these two, obviously AB, you can also make it 1, 2, 3 if you are comfortable, so that you can differentiate. So here S1 is max, after that it is S3, and at last it is S2. So it is for AB, it is for A3B, and then we have AB2. So option D, that should be the correct option. But again I am saying just look at this value, it is at last, so you can choose it. Okay. Now in this problem, this is basically not involving any calculation, but this is very tricky and interesting also. So what it is saying, when different types of salts have nearly same solubility product. So suppose you have salt 1, you have salt 2, you have salt 3. Now for all these salts, Ksp same. That is already mentioned, solubility product same. And this information is very important, that is given within third bracket, because less than 1 means it is always less than 1, because if you just look at this table, I just want to show this table again. So it is always lesser than, right? Now when it is lesser than 1, but still it should be mentioned in the question, then what happens? It is asking the most soluble salt is the one which is producing maximum number of ions, minimum number of ions, more charge on ion, or none of these. Now there may be different types of salt. Suppose I am writing AB, or it may be AB2, it may be A3B. So in the first case, you are getting 2, 1 cut on 1, 2. Here you are getting total 3. Here you are getting total 4. So, and accordingly, the value change. That is, in this case, it is a square, then it is 4s cube. Remember, in this case, it is 27s4. That means the number of ions increasing, the formulas are accordingly changing. So, in which case, this the most soluble salt is which one? Now, most soluble salt means what? Where S is mass. So, this S squared value, then 4s cube value, just consider the previous problem. In the previous problem, here we have 4s cube, s square, and 27 is 4. Okay, for these three different formulas. But suppose in all these three cases, KSP is same and KSP is lesser than 1. Now, when it is lesser than 1, simply I am taking a value. Suppose it is 10 to the power minus 16. Another case, it is 10 to the power minus 10. Now, when you are, that is, you are calculating S, whether it is S square, 4s cube or 27 is 4, whatever it is, whenever you are taking the value of S, and these are the values of KSP, there may be any value before 10, that is not important. Important is this power. Now, when suppose it is equal to S square or S cube or whatever, or 4s27 is 4. But when you are taking root over root of these or cube root, then it will be always, the value will always be lesser than this. Sorry, greater than this. That means if it is equal to S square, S will always be equal to minus 8. Similarly, suppose in this case, it is also equal to S square. So S will be equal to 10 to the power minus 5. So when this negative power, it is very high, the corresponding S, it is also obviously lesser than this. Now, suppose in both cases it is same formula A square. So from the first one, KSP value is 16, and here also, okay, I will take one example where KSP value should be same. So let me take another example. So KSP value, suppose in both cases it is 10 to the power minus 10. So when it is 10 to the power minus 10 and you are having formula like A square, another one is producing more number of ions, S cube, and it is also 10 to the power 10. So obviously here the S value is 10 to the power minus 5, and here the S value that you will get, obviously this S, suppose it is S1, this is S2, it will be something which is greater than 10 to the power minus 5, because now it is divided between 3s. Here it is divided between 2s, so it is 10 to the power minus 5. But when it is divided between 3, obviously S2 value, it will be something near about 10 to the power minus 3. And as there is negative sign, so 10 to the power minus 5, obviously it is smaller value than 10 to the power minus 3. So more it is distributed among more S values, so the solubility is basically increasing. So it means when it is producing maximum number of ions, then the solubility value, that is basically increasing. So in this case, S2 will be something which is greater than the previous value. So solubility is high. So that is why the first option, that will be the correct option. At a first glance, it seems that different KSP values. So when it is producing more ions, now the KSP value, it is distributed among more S. So it will be low, but actually it is not so. And why it is? Because it is lesser than 1. So when you have 10 to the power something negative and you are breaking it in more S values, obviously the individual S values, it becomes very high. But similar thing, if you do for positive power of 10, it will be reverse. But as we have negative power, so that is why here it will be, correct answer will be where it is producing maximum number of ions. So same KSP value, but as you will move towards high number of ions, from maybe 2 ions to 3 ions to 4 ions, then the solubility value, that will basically increase. So the most soluble salt is the one which is having maximum number of ions. The same problem can be constructed in a different way. Suppose it is framed in a way where these three different formulas are given, and it is asking that for all these three formulas, Ksp value same, in which formula solubility is max. So it will be this one. Or there may be, suppose, order, which will be having maximum solubility. So it will be A3B, then AB2, and then A. So the same concept question may be framed in different way, and you have to be aware about this. Okay, and this is true because it is lesser than 1. Now here it is clearly mentioned in the question, but even if it is not mentioned, you have to understand it, because for spending soluble salt it is always lesser than 1. It cannot be greater than 1, otherwise it will not be sparingly soluble salt. Okay, so this question is not involving calculation, but this is very conceptual question, very tricky question, and obviously very interesting. Okay, so we'll end the session here. Thank you for listening.